session is on advanced heat treatment for high performance toolings, and for this I have Mr. C. Vijayakumar, Senior Manager, Technical and Value Added Service, voestalpine High Performance Metals India Private Limited, joining us. May I please request him to join us on stage? And ladies and gentlemen, please join me in welcoming him up on stage. This is your clicker.
Thank you so much. So good afternoon, all of you. So many thanks to TAGMA for organizing event International Tooling Summit 2022, which is successfully ongoing. And this is the right platform to exchange our ideas, to make it more successful. We learn together, we work together with our tool rooms, we grow together. So such a platforms will really create an opportunity for us to demonstrate the success stories of us as well as learnings from the tool rooms. So today's topic in front of your screen is advanced heat treatment for high performance toolings. Heat treatment is a very generic topic. You might have aware about it. Tooling industry cannot surpass or bypass the heat treatment in quality, in terms of delivery, in terms of cost. So most of the gentlemen in the yesterday's session as well as today's session more worried about the delivery part, and they have a very confined timings to the heat treatment. Heat treatment is a topic where we need to spend some time, where our high performance tools, we made it fit for dimensionally, geometrically, we fit for all with respect to the drawings, but we need to give sufficient time in heat treatment to improve the tool performance. Of course, quality is default, everyone was agreed. So in these topics of discussion, I would like to cover in 4 segments, in short brief. Vacuum heat treatment and insight, retained austenite in tool steel microstructure, experimental analysis of BÖHLER K340 in cryogenics, and our success stories in cryogenic treatment. So when we call it as advanced heat treatment, which does not completes at the room temperature, it takes to the lower temperature, which is below the room temperature, could be in hundreds of minus degrees centigrade, which is the cryogenics temperatures. So let us go through the first topic of vacuum heat treatment, just an insight. And in this topic, there are certain influential factors I would like to confirm with you that about the steel and heat treatment. The hardenability. We know that we select a tool steel for certain segments, for press tool applications. We have a different specification of hardness based on the application requirements. So first of all, the hardenability of the tool steel has to be achieved. The ability of the material to get hardened in this perspective. And compressive strength of the material is also equally important. And then distribution and dissolution of carbides when we do the heat treatment is also equally important. Of course, last but not least, that selection of right parameters is also equally important. These are all the minimum parameters which highly influences your tool performance to demonstrate your products with your customers. So let us go to the first topic of vacuum heat treatment and insight. We call it as a heat treatment is a special process. We won't call it as a tool manufacturing is a special process. But in the tool manufacturing supply chain, heat treatment is a special process. Why we call it as a special process? The process which cannot be quantified, the results, when it outcomes from the outward inspection. The results cannot be quantified at the time of dispatch from the heat treatment shop. We have a certain limitations in heat to qualify the heat treatment. One thing everyone knows that hardness. If the material is having so much of hardenability, yes, we can achieve the hardness. But it does not limit only to the hardness. So this requires certain validations to complete the total process. So instead of inspection, that needs certain validations. So there are 2 types of validations which normally do when we want to differentiate. One is the furnace validations. There are certain standards and specifications whose details it talks about it. So for the tooling industry, we need to make ourselves the vacuum furnace within plus or minus 5 degrees centigrade so that the temperature uniformity will be there in all the locations. So tool being a complex process, tool, steel, and tool profile being a complex in nature, we have a differential expansion thermally when we do the heat treatment. So we need to ensure that the thermal hot box is completely uniform in all perspectives. Of course, there are certain process validation. We are different grades of materials going to be heat treated for cold work tool steels and high-speed steels, which is having different alloy chemistries. So the final hardness makes very important, and we qualify through the final hardness and quality of tempered martensite. If you want to check the heat treatment, as I said, that you can measure the hardness, and if you want to check the microstructure, if you give it to external laboratory, once the microstructure is achieved 60% of its capability of martensite, they say it's tempered martensitic structure, but that is not enough to do or complete the total quality of heat treatment. Of course, there are certain transformed products. There are byproducts when we do the heat treatment, which comes from austenization to the quenching temperatures. Those byproducts have to be avoided. There are certain byproducts will be there in the material during heat treatment that can be there. There is no issues. But there are certain detrimental byproducts which has to be avoided in heat treatment. So such a type of validations has to be done for the heat treatment, so we don't want to depend upon inspection process. I'll just give you a brief idea about what could be the difference in bad heat treatment and fair heat treatment. Proper heat treatment makes sense. Bad heat treatment, everyone will understand as a layman thought. If suppose there is a deviation in the systems, if suppose any deviation in the process, if the parameters was not completely followed as per the recommendation and suggestion, that will lead to your bad heat treatment. And what about the fair heat treatment? Here, this makes something difference. Right selection of parameters could be the fair heat treatment. Then we need to define what could be the right selection of parameters. If the tool steel manufacturer specifies the range of hardening temperatures from 1000 degrees centigrade to 1100 degrees centigrade of band, for an example, you are supposed to do at 1000 also, you can do at 1100 also. So if you see the microstructure gives a clear picture, the total mechanical properties or physical characteristics, whatever it be, it will be up to the level and optimum conditions. This is termed as a fair heat treatment that everyone knows. And what could be the advanced heat treatment then? What could be the differentiation? So it comes not only from the metallurgy, it comes from the tool shop. It's come from the application intent. So if you know the technical know-how of application, accordingly you can choose the hardness, accordingly you choose the process parameters, you will be more choosy what is the hardening temperature for a particular tool. Because tool is a complex in nature. When it works, suppose for an example, press tool applications, there is a biaxial stresses, there is a triaxial stresses, there is a shear force, there is a bending moment in drawings. So considering that as an application perspective, thinking on application perspective, we would like to arrive certain temperatures to be fixed for this heat treatment. So if we do such heat treatment, that can be termed as advanced heat treatment. In voestalpine high performance metals, we do in such way for the critical applications, we will be more choosy in select of hardening temperature. So that's a definition for advanced heat treatment. As I said, there are certain transformation will not complete at the room temperature. It requires the lower temperature to get it complete. And also I said, there are certain byproducts which could be later detrimental in your performance, which could lead to detrimental performance when the tool is working at press. So those things has to be avoided. Let us talk about something on retained austenite in microstructure of tool steels. If you see in left to me, I think the soft annealed microstructure at the raw material stage, the condition of ferrite plus alpha carbide, the mostly belongs to the 12%, 15%, 20% of alloy carbide materials. Goes up to high-speed steel. If you see BÖHLER S600, BÖHLER S590, S790. Those grades will goes up to 30% of alloy carbides. So alloy carbides, which is in spheroidized form, plus the ferrite matrix, when you take it to the austenizing temperature, what will happen? The undissolved primary and secondary carbide will be there. We required these two guys, primary and secondary carbides, for your tool performance, because this is the intent to get out the wear resistance of the materials. And it should be equally distributed and uniformly. So the saying is, austenite is the phase where we call it as a hardening temperature. We take to that phase temperature, say around 1000 degrees centigrade, maybe up to goes to up to 1200 degrees centigrade. We have to cool it drastically, as fast as possible. This is a thumb rule for the heat treater can quench as fast as possible. I think you may aware about it. There is something term called as a supercooled liquid. Supercooled liquid. Your car, like a four-wheeler car glasses, which is called as a supercooled liquid, where it retains the same position at the melting temperature. We won't say it as a solid, but if the metal at a melting temperature, when it quenched to room temperature, if we have the metal as a metal at 0 time, that's called as a supercooled liquid. So such a fast cooling rate, even in heat treatment, is needed to achieve the final mechanical characteristics. So the completion of these phases from austenite to martensite will never take place at room temperature for cold work tool steels, most of the cold work tool steels and high-speed steels. There are certain poisonous content which is deterioration, which will be detrimental for your application, will stays back, that is called as a retained austenite. Now, if you want to improve the performance 15-20% with the same value, with the same effort you made a tool manufacturing, if you want to improve the further performance, you need to convert this retained austenite into complete martensitic structure. There is a limitation. How to control? We need to measure this. How to measure this? There are certain limitations in the measurement. Up to 2%, 1 or 2%, we cannot, that's away from the detection limit. So to ensure that it should be reduced to close to 1 or 2% to get a maximum out of it. So what will happen, as I said, the byproducts, if you cool it too slowly, such ferrite and carbide precipitations and pearlitic structure will happen. If you a little bit fast cooling, you may end up with certain characteristics of bayonet, which could be the upper and lower. And if you drastically cool as fast as possible, you can end up with martensitic structure, which is the intended microstructure for our heat treatment. So that top one could be more soft. That can be useful for further mechanical work scenes in the steel mills, but that may not be applicable for our tool steels. So what the tooling fraternity will think about the retained austenite? They think about that there could be some reduction in hardness, something lower dimensional stability if they want to do further value addition like PVD coatings. So they think that dimensionally it may not be stable, there will be expansion and contraction because of these poisonous things inside the material, and that may lead to catastrophic failures. What the metallurgist will think on their own way of, they say that it's an incomplete transformation. So there is 10% of retained austenite is stayed back. I couldn't able to convert it, and this is a metastable, unstable retained austenite that can be a multifarious functions. Of course, that affects mechanical properties. The heat treater, finally it comes to the heat treater. The metallurgist says something, the tooling fraternity says something that the tool may get failure because of heat treatment, have a detection of 5% of retained austenite in your tool steel. Then the heat treater will be on the trouble. So the heat treater, on his perspective, what he will think is, he thinks how to control or avoid retained austenite. Sometimes it's very difficult. We cannot eliminate everything, the antibodies in our bodies. So how to control the retained austenite? How to measure it? So this could be the thinking of heat treater. Now, the heat treatment is not get completed at the room temperature. And also we know that the retained austenite is a multifarious component which is detrimental for the application of tool steels or tooling applications. For an example, just for your understanding, if you see the picture, BÖHLER K340, which has been fairly heat treated at the recommended temperatures, The hardness was 62 HRC. The retained austenite is closed up to 3.5. The proper heat treatment, what I said is this. The water temperature that retained austenite is 3.5. And the BÖHLER K340 on the other side, this being heat treated at 1100 degrees centigrade. We have a retained austenite of 13%. And then if you see ASI D3, the retained austenite up to 85%, where you could not able to convert. So the thing is, conclusion is incomplete transformation from austenite phase to martensite phase during heat treatment. Just jumping to the third topic of experimental analysis and response of BÖHLER K340. So now we know that what is the advanced heat treatment and what could be the multifarious component in tool steel after heat treatment is retained austenite. We know that retained austenite is detrimental for the tooling performances. Now I would like to show you that we have done certain experimental analysis with Indian Institute of Technology, Mumbai, and how it responds to BÖHLER K340. So cryogenic treatment is an ultra-low temperature treatment, nothing term called as cold in the universe. It's a lack of heat. As we say normally, nothing term called as dark. It's the absence of light. In same way, there is nothing term called as cold. It's absence of, there is a lack of heat. When you see the heat, when the heat goes off, when the heat negative, the Q is negative, that could be the exothermic reaction. And when the Q takes the heat, is endothermic reaction. So here everything is exothermic reaction because it's happening at the lower temperatures. If you see the microstructure, this is very generic microstructure on the two ways. There is no issues, evenly distributed. If you see the microstructure, there is a newborn babies. If you see the microstructure in K340, BÖHLER K340, you see the white marks which has been arrowed up is the newborn babies resulting from the cryogenic treatment at ultra low temperatures. What it will do, it improves the cohesiveness of the matrix. It increases the bonding strength of the matrix so that the carbides will be more thermally stable. If you operate 60 strokes per minute, 100 strokes per minute with two axial stresses, that could be giving the benefits. It promotes dimensional stability, of course, overall durability of the component. The final, last but not least, the success stories. The success stories of cryogenic treatment. If you see the knives, the failure mode is wearing out and breaking and everything, the life performance increased by doing cryogenic treatment 25 to 30%. This is again from BÖHLER K110. The application is plastic paper cups and plates. The performance increases 35 to 40% with BÖHLER K110. This was soft gelatin capsule machine elements made out of AZD2 and K110, and overall percentage increase is 25%. Same thing for the cutting blades and knives for the different customer. Here the powder metallurgical version. Powder metallurgical version of BÖHLER S392 will always give the additional performance in the raw material stage and as well as if it is properly heat treated. And when we do the cryogenics, it has improved to another 20 to 25% of performance. Of course, aluminum extrusion die also have a good case study of comparing AZD2 and K340, which are around 25 to 30% of performance. And for the tablet tooling, the emerging segment nowadays, they are making attempt for the new premium grades, BÖHLER K340, Wuthegom, Sleipner. So these materials will really improve the performance when they do the proper cryogenics. There also is 25% in the stamping tools by using Wuthegom, Sleipner. So choice is primarily based on the steel, and the choosing of steel depends upon the application requirements. So we need to understand the application requirements based on the failures. So try to address the failures, try to find a solution, and then select the tool steel accordingly, and then insist the heat treaters to select the process accordingly. Still the quenching is needed at the ultra low temperatures. Thank you so much for your patience and listening.
Thank you so much, sir, for that presentation. May I please request our Vice President, AGMA India, Mr. Shanmuga Sundaram, to please join us on stage and hand over a memento. Thank you so much, sir, for that wonderful presentation. I'm sure that if you have questions, you could engage with him during the networking breaks. Ladies and gentlemen, would you please join us in thanking Mr. C. Vijayakumar for that fantastic presentation?